All right, hello everyone. Welcome to the next lecture, next part of the lecture number 7. We started to talk about the step response of a parallel RLC circuit, and in this part of the lecture, we're going to do some example problems. Again, very briefly, here's a parallel RLC circuit and the step response. In the step response, right, we bring in a DC current source in the circuit. So initially, in order to solve that, again, this is going to come out to be a second order circuit and a second order differential equation. When we apply Kirchhoff's current law, we ended up finding out this second order differential equation for the inductor current. And then we said that in order to solve this inductor current, we have to find the voltage. And then we ended up figuring it out that here is our differential equation for the voltage. And this differential equation was exactly similar to the natural response of the voltage. So we looked at here are the three solutions of the voltage for that second order differential equation. So then we use these three solutions and put them back in the equation which we found from the KCL right over here. And once we did that, we ended up finding these three solutions for the inductor current. And one was for overdamped, underdamped, and critically damped. So this was kind of an indirect long method. The direct method uses this kind of a principle which states that for a second order differential equation which has a constant forcing function, the solution of that will be equals to the forced response plus a response that will be very similar or very similar in form to the natural response of the circuit. So for example, over here we have the current value and the voltage value, and the answers or the solutions of the current and the voltage, again both of them were originally second order differential equations. The solutions of that will be equals to the forcing functions, right, which in this case is going to be your final values if and vf, and then the functions which is very similar in form to the natural response, right? It's not exactly the same, it is similar form, so which means that it is going to have different constants. And as you have seen in the indirect approach, we ended up getting these primed constants, which can be a combination of those others ones, but we are interested in those primed constants which we can directly find. And then we also looked at, in terms of a summary of this table, that we can practically use this table to find a step response of any parallel RLC circuit. And then really the idea is to start with finding the initial conditions, V naught and I naught and IF, since we are talking about a step response. After finding those conditions, you have to find the value of the alpha and omega naught. And based on how these two looks like, right, for example, in case of overdamped, if your alpha square is greater than omega naught square, your response is going to be overdamped. In that case, you have to use this equation. This is going to be your inductor current expression. And in order to do that, you have to find the values of A1 and A2. Before, you have to find the values of S1 and S2, so you can use this roots of the characteristic equation to find S1 and S2. And then, of course, find the values of A1 and A2. And in order to find the values of A1 and A2 in overdamped case, or in case of an underdamped, you have to find the values of B1 and B2 dash. And in critically damped, you have to find the values of D1 dash and D2 dash. In order to find any of these prime constants, you're going to need two equations, right? Where those equations are coming from? By solving for IL0 positive and DIL0 positive over DL. And here are those two equations that you don't need to redrive again unless I ask you an exam to drive them. You can practically use these equations to find those two variables. Once you find these variables, you have to just put them back in these main equations and you should be good to go. Okay, so let's get started with our example problems today. Okay, so just let me open a tab with slideshow from current. Okay, so here's the first example problem, and this example problem states that here is a circuit. It's exactly the same similar circuit that we have used to make the derivations. It says that at t is equal to 0, your DC current source is 24 milliamperes, and then the value of the resistor is 400 ohms, and we have to find the value of the inductor current. It does another thing important is it also states that over here, right? So whenever you have to find, right, the step number 1 is you have to find the value of the V naught and I naught and IF, right? So V naught and I naught are the initial conditions, and this is IF, which essentially you find is when the circuit approaches the next steady state value where t is equal to infinity. It doesn't go all the way to infinity, right? And as we're going to realize that the final value is very close to the final value comes very soon, depending on a few taus. Okay, so coming back to the circuit, we have to find the initial conditions, V naught and I naught. What is the value of the V naught and I naught? Either we can find those values by solving the circuit at t is less than 0, or we can look for that information in the question. If that is not given in the question, then we have to find it by solving the circuit. Okay, over here, it says that the initial energy stored in the circuit is 0. So this means that V naught was 0 volts and I naught is 0 amperes. Okay, then let's find the value of the IF. What is going to be the final value of the current? When we're going to reach, in the step response, we're going to reach the next steady state, next final state. At that point in time, your capacitor is going to become open circuit and inductor is going to become short circuit, right? So your capacitor will become open circuit and inductor will become short circuit. So if the inductor is going to become short circuit, this entire current is going to flow through inductor, right? So IF is going to become 24 milliamperes. Okay. So that's really the first step, where we end up finding the initial conditions and the final value of the current, because these are the variables that we need in order to solve the equations, right? Step number 2 usually is, in order to find the inductor current, as we have seen in that beautiful table, or even if we don't remember the table, we should be able to easily figure it out what the steps are, right? Then second thing that we have to do, and we have been doing it for a while now, we have to find the value of alpha and omega naught, right? So find the value of alpha and omega naught and then compare how they equate to each other, whether one is greater than the other one or equal, right? So alpha is 1 over 2 times RC, 1 over 2 times resistance is 400 ohms, capacitance is 25 nanofarad. The value of the alpha, if you're going to solve this, is going to come out to be 50,000 radian per second. Okay, so nice. Let's find the value of the omega naught. Omega naught is 1 over square root LC, or square root of inductance, 25 millihenry, into capacitance again, 25 microfarads. Okay, nanofarad, sorry, 10 to the minus 9 nanofarads. Okay, and your value of the omega naught is going to come out to be 40,000 radians per second. So as I can see, my value of alpha is greater than omega naught, right? So alpha square should be greater than omega naught, practically. So this means that I am going to have an overdamped response. Overdamped response. Okay, let me show you again, going back to the table. Right, so if we get an overdamped response, all I need to do is to pick up these equations. Right, so here's an overdamped response, here's an underdamped response, here's a critically damped response. I'm going to pick up this equation, and then I have to find the constant using these two equations. If my response would have been underdamped, I'm going to pick up this equation and use the rest of the two equations to find the prime constants. Essentially, these are the next steps, and then we can literally solve anything. Okay, so once I figured it out that my response is an overdamped response, so what we need to do is, I need to write down the equation of the inductor current. So the equation of the inductor current is IF plus A1 prime e raised to power S1t plus A2 prime e raised to power S2t, right? Again, t is greater or equals to 0. So here's my equation. In order to find this expression, I need to find the values of S1 and S2, and also A1 and A2, A1 dash and A2 dash, and IF. I already know the value of the IF. I'm going to first find the values of S1 and S2, and I also need to find the values of A1 and A2 dash. So let's start with finding the values of S1 and S2. Again, S1 and S2 are the roots of the characteristic equation. Right, and we know that S1 S2 equals minus alpha plus minus alpha square minus omega naught square. So S1 is going to be equals to minus alpha, which is minus 50,000, plus square root of alpha square, 50,000 square, minus omega naught square, minus 40,000 square, right? And if you're going to solve this, you're going to be left with S1 equals to minus 20,000 radian per second. Let's find S2 as well. Minus alpha minus 50,000 minus 50,000 square minus 40,000 square, and S2 is going to come out to be minus 80,000 radians per second. Okay. So again, this was an equation. The very first step is I need to figure out which equations to use, which inductor current equation to use, and how to determine that. I need to figure out which my response is going to be based on alpha and omega naught value. So once I figured out that I need to use this equation, then practically I'm just finding those constants based on the equations that I can easily derive in a few minutes, or I can look it up in the table. So once I find the values of S1 and S2, next thing to do would be to find the values of A1 dash and A2 dash. And again, those are also written in the in that table. So the two equations that I'm going to use again is, the one is IF plus A1 dash plus A2 dash equals I naught, and S1 A1 dash plus S2 A2 dash equals V naught over L, right? So I know that my I naught equals to 0 and V naught equals to 0, right? I naught is 0 and V naught is 0. So that is why both of the right hand sides is going to become 0. And then I also know that the final current is 24 milliamperes, right? So 0.024 plus A1 dash plus A2 dash equals to 0. And my S1 is minus 20,000, A1 dash, A2 is minus 80,000, A2 dash is equal to 0, right? So of course you got two equations, you can solve it for A1 and A2. The value of the A1 is going to come out to be minus 32 milliamperes, A1 dash, and A2 dash is going to come out to be 8 milliamperes. So now you find the values of the A1, got the values of the A1 dash, A2 dash, S1 and S2. You can easily plug all of those values in back into the inductor current equation. Again, inductor current equation was IF plus A1 dash e raised to power S1t, e raised to power S2t. Once you're going to do a few example problems, you're going to start to actually remember most of this formula. Okay, so let me plug in all the values. So IL of t equals to 24 milliamperes. I'm going to write the overall current in milliamperes. So 24 plus A1 dash is minus 32 e raised to power minus 20,000 t minus 80,000. A2 dash is 8 milliamperes minus 8 e raised to power minus 80,000 t. And yeah, and again this should be equals to milliamperes at t is greater or equals to 0. Okay, so this is how you can find the value of the inductor current as well. Okay. Sorry, one thing over here is your value of the A2 dash is plus 8 milliamperes, so this should be like this. Okay, again, in order to solve any step response of the circuit, literally what you need to do is to first figure out what the initial conditions are. After finding that, find out the values of alpha and omega naught, then figure it out which response it is, pick the right equation, and find those constants. We're going to do this process again, and we're going to realize that now our response is going to be different. So we're going to do this similar exercise very quickly. Okay, so sorry, just give me 1 second. Okay, I'm gonna maybe separate this lecture into another part. All right, sounds good. Thank you.